So we said last time that in calculus, or in math rather, there are always three ways to solve a problem, right? And what were some of the ways that we talked about last time? Numerically, graphically, right. Right. So in the first section, in section 12.1, we talked about how to find limits graphically and also numerically. Today, we're going to do the same thing, but algebraically. All right? And we've got a few properties here that help us do that. And we can definitely get a very precise answer. And all three of these methods are equally viable. Okay. We've got a couple of properties that help us do this. And here they are. Now, no one really is going to ask you to these aren't properties that you memorize like a formula sheet or whatever. These are ones that you will inherently be using as we do this stuff. And you're not even going to know that you're using them. However, if somebody ever stops you and asks you to justify why you're doing what you're doing, you can just refer to these as backup. Okay? All right. Let's take a look at one. The sum property. Okay? So suppose you're finding a limit of something plus something else. What you can do is divide and conquer, meaning you can find the limit of the first thing independently, and then find the limit of the second thing independently, and whatever you get, you add them to each other. What do I mean by that? Suppose you want to find the limit of 3x squared plus 5x, okay? And you want to find the limit as x approaches 2. You divide and conquer. What you do, you say, oh my God, this is so much to tackle at once. I'm going to find the limit as x approaches 2 of what? Just that first one, baby steps, 3x squared. And then you say, okay, now I'll find the limit as x approaches 2 of the second one, 5x. Whatever I get from the first calculation and whatever I get from the second calculation, I just add them, and that's one way of doing it. Okay? Yeah.
What if one does not exist in the other one?
Okay, so we'll go through like a whole bunch of stuff right now, and you'll see. All right, so that's the same thing is if you had two things that were being subtracted. So if you wanted to find the limit of f of x minus g of x, so if it was 3x squared minus 5x, you would just do the same thing. Product property, quotient property, you do the same thing, right? Do the first function's limit, and then find the limit of the second function and multiply them, or divide them. Same situation. What was a scalar? Anybody remember what a scalar was? A scalar is, as opposed to a vector, what is it? It's just magnitude without direction, and in math, without purposes, it's basically just a number, okay? Like a 5, a 3, a -1, okay? So if you have a number times a function, you can move it out, you can find the limit of the function, then multiply it by that number. So moving along, I think it's more useful if we just apply these to an example. And the example that we're going to apply it to is this. So we need to find the limit as x approaches 4 of 6x squared minus 6x plus 3. I'm going to divide and conquer, okay? So I will say, okay, first I'm going to find the limit as x approaches 4 of the first one, 6x squared. Then I'm going to find the limit as x approaches 4 of 6x, and I need to subtract these because there is a minus in the middle. Plus, I'm going to find the limit as x approaches 4 of 3. Yes? Now, let's do a little bit more simplification. We can move the 6 out. So it's 6 times the limit as x approaches 4 of x, and I can also move the square out. Okay? minus, I can move this 6 out, times the limit as x approaches 4 of x, plus the limit as x approaches 4 of 3. Now, let's just focus on this. You've got the limit of this function, and the function happens to be 3. So imagine your function is just 3. Okay? You have y equals 3. Imagine what the graph of that would look like. What would the graph of y equals 3 just look like? A horizontal line. So now visualize that graph. Now think, when x is getting closer to 2, what would the y value be? 3. What about when x is approaching 10? What about when x is approaching 1,000,000? Or when x is approaching a 4 is a 3. So this is just 3. Now, let's visualize an equation, y equals x, and let's think about the graph of that. What does the graph of that look like? It's a diagonal line with a slope of what? 1. So basically it looks like that. So it's got a direct relationship with x, right? So when x is 1, y is, when x is 10, y is, when x is 4, y is. So as x is getting closer to 4, y is getting close to 4. So then if you just have x, the limit is just that number, times 6. So minus 6 times 4. And here what I have is 6 times, again, the limit as x approaches 4 of x, which we said was 4 squared. And now I multiply, I add, I subtract, I do the exponent, blah, 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 blah. And I get 75, meaning the limit is 75. Okay? Had you graphed this function and looked at, what the value of the graph is approaching as you approach 4, sure enough, it will get closer and closer to 75. Okay? Yeah.
Kind of like confused of where the 6 is from. I know where the 4 and 3 are from. Just from there.
6x squared and minus 6x.
Okay.
Now, yeah. Well, as fun as this may be, it's tedious. So I don't have to do it every single time. In fact, we do it once, and then we never do this process again. Because of this cute little property that says, if p of x is a polynomial, and c is a real number, then the limit of this polynomial as x approaches c is just the value at c. So basically, all you really have to do is plug in the number. Did you still have a question? Are you sure? Okay. So now, all I'm going to do for these is use direct substitution. There's even a name for it. So, all I'm going to do is take this number and substitute it for x. So this is 2 minus 3 over 2 times 4 minus 2 minus 15. Now, the minute you substitute your value, you can drop that limit notation. Okay? So this is going to be what on top? Negative 1 over what? Negative 9, which is just 1 over 9. Okay? We could have totally done it the way we did in example 1, but this is so much more useful. All right, do the next one. What do we get? Right, we plug in negative 1, so it's negative 1 plus 3, which is equal to root 2, and that is the limit. At any given time, answers in fraction form, simplified fraction form, or simplified root form are always more preferable to decimals. Okay? Always. All right, let's look at this one. Negative 8. As x approaches negative 8, what do we get? Well, we put negative 8 in there, and we get the square root of negative 2, which is an imaginary number, but think about this. So think about this. How can the value approach some imaginary number? It can't. So we say this is DNE for does not exist. But let's explore exactly what is happening. See, this is why a graph like gives you a clearer idea, because you see exactly why it's DNE. So show me, what does a square root graph look like? Right? Yeah. Now, this one though is the square root of not x, but the square root of x plus 6. So what does the plus 6 do? It moves it to the right or left? Left, 6. So it starts at -6 and goes that way. Now I'm being asked for the limit as x approaches -8, which is here. Okay? There isn't even any graph there. That's like barren desert land. Okay? So there is nothing there. That's why it doesn't exist. Okay? So other reasons might be what? What do you think some other reasons might be? That a graph might not exist. The limit might not exist. Right? That's here.
Maybe it's not a real number.
Right? Other than real or imaginary. In what other cases? What? When you were looking at the graphs before in section 1, what were some of the cases where you got?
It's like something about
Right, when the graph approaches different locations, when there is an asymptote, right? Right. So now, if you happen to get something that looks like this, 0 over 0, this is not what we got before. If you happen to get 0 over 0, I'm not talking about a number over 0. That is completely something else. If you happen to get 0 over 0, okay, we call this indeterminate form. Because, yes, we don't like to divide by 0, but what if you have 0 over 0? In this case, there is a lot of information that we are not able to gather, and hence the term indeterminate, because it cannot be determined what this is going to look like. So, well, no. So we have to sort of neutralize the situation. We have to first figure out what is it about this equation that gave us 0 over 0, and then we have to get rid of that part. And once we do that, there can be two possibilities. It's either, DNE, or it very well might exist. You might get a cute little number like 3. Okay? So when we do this, it's necessary to use other methods, and it's possible that the limit exists, or it might diverge into negative or positive infinity. So there are two possibilities. So it's still not game over when you get 0 over 0. Here's one example. So here's one of the things you can do to neutralize this 0 over 0 situation. One is factoring. So what you do first is this. You're given this function, and you want to find the limit of it as x approaches to -2. The first thing you do, always, is plug -2 into this. And when we do that, we get -8, minus 3 times 4, minus 4 times minus 2 plus 12, over 0. Well, the numerator, as it turns out, is also 0 over 0. This is indeterminate form. Okay? So we need to work with this. Well, this is a rational expression. We see if, this can somehow be factored. So let's try to factor this. This is going to be the limit as x approaches -2. Now, one thing about notation. When you're going to modify algebraically the expression that you're working with, you have to carry this limit with you at each and every single step until the very end when you can actually plug in a number. So now, how can we factor the numerator here? Grouping. Right, so we're going to group this here. First, we can factor out an x squared. And then I get minus 4 times x minus 3. This is equal to the limit as x approaches -2. I write the common term here. Okay? So I write the common term, and I've got left x squared minus 4. Now, this is the limit. As x approaches negative 2, I can factor that further, right? It's x minus 2, x plus 2, over x plus 2. They go away. Okay, you made it go away. You made the denominator go away. When you plugged in negative 2, it was giving you a 0, but now you made it go away, so you've already neutralized your situation. So now all I'm left with is the limit as x approaches negative 2, x minus 3, x minus 2, and now, can I plug in negative 2? I can. And I get negative 5 times negative 4, 20. So that's my answer. Okay? So even though I started with 0 over 0, which was indeterminate, I still ended up getting a cute little answer. Okay? All right. So let's do this. Let's plug in 6 on the top here. We get 0 in the numerator over 3 times 36 minus 66 minus 42, still 0 here. So that's indeterminate. Okay, this isn't going to work. What do we have to do? Factor. So go ahead and factor here. I'll pause this for a few minutes. Go ahead and factor, and we're going to come. When we factor, we get x minus 6, x plus 1, 3x plus 7, x minus 6. Cancel it out, and this is what we have. Now I can plug in my x equals 6, and what do I get? 7 over... So I plug in x equals 6. This is 7, and what is this? Oh, it's minus. Sorry. But this is 3x plus 7 here. So it's 25, which is 1 over 5. Okay, so that's one situation. All right, let's take a look at this next one. We're going to plug in x equals 25. So here I get 0 because it's 25 minus 25. And here I get root 25 minus 5, which is what? 0 over 0, right? Okay, that's not going to work. So factoring isn't going to get me anywhere either because I can't factor any of these. Meaning, I need to rationalize. I need to get rid of the square root. Okay? Now here's how we do this. This is the limit as x approaches 25 of x minus 25 root x minus 5. Now, the denominator is the term with the root, so I need to get rid of that. What can I multiply it by? Root x plus 5, and what do we call that? Yeah? The conjugate, right. Now, in the denominator, or rather where you have the roots, right, what do you end up with? You end up with a minus b, a plus b. So to multiply, you're going to take the first term and square it, which gives you x. Second term and square it, 25, with a minus in the middle. Now, in the numerator, as much as you want, you've got this urge to FOIL, and because it's so much fun foiling with these roots, right? But don't. Because if you just copy it over as is, right, you can actually cancel out in one shot your x minus 20. Ooh, I forgot the limit. Can't forget the limit. Yes. Okay. So this is now the limit as x approaches 25 of the square root of 25 plus 5, which is just 10. Right? So you see how we were able to get rid of that situation by rationalizing? Yeah. Well, no, I mean, there'll always be a way algebraically to cancel things out. Okay, look at this one. We plug in x equals 0, and I get 2 minus root 4, which is 2 minus 2, which is 0, over 0. So that's indeterminate. Yes? Yeah. Okay, we have to rationalize. In this case, the term with the root is in the numerator, but it makes no difference. So the limit as x approaches 0 of this, we multiply by what? Right. Well, what you do now, you square the first term. The first term is a what? It's a 2, and when you square it, you get 4, minus the second term is this root, x plus 4. And when you square the root, what do you get? Right. So this is the limit as x approaches 0. 4 minus x plus 4 in parentheses over x times 2 plus this. So this is the limit as x approaches 0. What happens in the numerator here? What do we get? Four minus x minus 4, which is 0 minus x, right? Over x times 2 plus root x plus 4. Now, what happens to the x's? The x's don't cancel out. They cancel out, and you've got a negative left. So it's negative 1 over 2 plus root x plus 4. Now I can plug in the 0. Right? What happens if I plug in the 0? Negative 1 over 2 plus root 4. Negative 1 over what? 4. Okay? Alrighty. Now, let's take a look at limits at infinity. Okay? Suppose you've got a function that looks like this, x to the power of n. Now, what happens as x approaches infinity? So, suppose you have a really large value of x. So, suppose x is about, 1,000,000. Okay? What happens if you raise that to a power? So, what if you have x squared? And now x is 1,000,000. What would happen if you squared it? Right, 1,000,000 times 1,000,000, which is a huge number. So if you have an infinitely large number and you square that, what kind of number do you end up with? Still an infinitely large number, right? Now, what if you've got something like this, but now you want to find the limit as x approaches negative infinity. So let's think of a number that is negative but very large, like negative 1,000,000, okay? Now suppose you take negative 1,000,000 and you raise it to the power of 2. It's positive, but how big or small is it? It's huge. It's a huge positive number. So what happens is, if you raise an infinitely large number to an exponent, okay? If the number is negative, and if you raise it to an even exponent, you get positive infinity. So let's think about this. Suppose you're looking at x equals negative 1,000,000, okay? And you raise it to the power of 3. Do you end up with a positive or a negative value? Negative. But is it large or small? A large negative number. So it's like negative infinity, okay? So if you've got negative infinity, or a number that is that big, to the power of 3, you're going to go to the negative infinities. Okay. Let's think about that. One other thing I want you to recall from before is this. Normally, in your math classes until now, we basically focus on the region very close to the origin, right? So, here, like the farthest out you go from the origin is like x equals 20, okay? So we're always in that vicinity. Imagine now, and we talked about this when we talked about end behavior, imagine now I want to expand, I want to move out, okay? Further and further out. Here, to where x is infinity, or when x is negative infinity, okay? Now imagine we're there at x equals infinity. Now imagine you've got an infinitely large number, like 1,000,000, and you raise it to the power of 6. Think about how big that number is. 1,000,000 to the power of 6.
It's a positive.
Now, but it's huge, right? Now imagine it's 6 times 6 zeros.
Oh, yeah.
Now imagine you take your 1,000,000 and you raise it to the power of just 5, not 6, but 5.
It's less than 6, but it's a lot.
But it's 6 less zeros.
Yeah.
It's 1,000,000 times less, right? So as you're talking about the infinities, something to the power of 6 and something to the power of 5 are completely different. When you raise 1,000,000 to the power of 5, it pales in comparison to when you raise it to the power of 6. So the moral of the story is, at the infinities, the only terms that really are influential are the ones with the highest power. Just the highest power. So if you look at this here, the only term as x approaches infinity, I'm not talking about when x equals 100 or 20 or 2. As x approaches infinity, the only one that has any power is that term 4x to the 6. So I can literally just get rid of all those. Those terms will be negligible when x equals infinity. No. Okay? So now this is just the limit as x approaches infinity of 4x to the 6. Now, here I have an infinitely large number raised to the 6. That's an infinitely large number still. And if I multiply it to the 4, that's an even larger number. So we're looking at positive infinity. Or you can say DNE, positive infinity.
What would you prefer?
The DNE.
That's fine.
Okay? But you have to put in,
Remember that.
but if you just say DNE, that's not right. Okay? You need to distinguish with the positive
Either one
infinity.
is correct.
Yeah. Here, look at this one. Which term are we going to take?
The negative x squared.
Right? Negative x cubed. So now, this is as x approaches negative infinity. Now imagine you plug in like a negative 1,000,000. To the power of 3, is that positive or negative? Negative. But there is also a negative here, so it's positive infinity. Yeah. Now what if you have rational functions? These are reciprocal functions, right? This is how reciprocal functions look like. Look at what happens here. As x approaches infinity here and here, what happens to these functions? Where do they go?
Keep going to 0.
They are going to 0, right? Now look at what we're going to do here. We're going to evaluate these limits. So here, it's going to be the same thing. The limit as x approaches negative infinity. Now what we're going to do is we're going to split up the numerator and the denominator. You might recall when we were talking about rational functions before and asymptotes, how did we find horizontal asymptotes? Right, but what from the top divided by what from the bottom?
Exponent.
The highest power from the top, the term with the highest power from the top, the term with the highest power from the bottom.
So is this not a whole?
So here, no, there is a big time asymptote here. So from the top, I take a 5, because that's all I got. Now in the bottom, which one is the term with the highest exponent?
No, X.
So this is like x to the 1 minus 10x to the 0, right? So it's x that has a larger exponent. Now, let's think about this for a minute. Yeah. Because you want to take the term with the higher exponent. So here, x has an exponent of 1. Here, this is 10 times x to the power of 0. That's how you get the 10. Right? Now. Huh? Okay, so you have to take something from the top. All you have is the 5. But here, it's not that we're ignoring the number. We just chose one with a higher exponent. There was something else here that overpowered, but there was nothing else here that overpowered the 5. Okay? Now, imagine you've got 5 pizzas. Okay? And you have to divide it among 5 people. How many does each get? 1. Now imagine you're not dividing it between among a group of 5, but you're dividing the 5 pizzas among a larger group, 10. How many does each get? Half. Now imagine you have to divide it between 30 people. How many does each get? Much less. Now imagine you have to divide it between 5,240 people. Much less, right? Each person gets much, much less. What if you had to divide it among 1,000,000 people? Those 5 pizzas divided between 1,000,000 people. How much, like, think about, just visualize how much each one would get. That is a tiny little speck.
You don't even get to see this speck.
So, right. So the moral of the story is, as the denominator gets infinitely large, what happens to this entire thing? It gets infinitely small, close to 0.
So they're indirectly.
So then this is 0. So as we approach infinity, as x approaches infinity, that whole fraction approaches 0. And you can see it on the graph, right? As you approach negative infinity, the function approaches 0. As you approach negative infinity, the function approaches 0. Now, let's look at this one. We're going to do the same thing. The limit as x approaches infinity of the term with the highest power is this. And what's the term with the highest power on the bottom? So this is the limit as x approaches infinity of what? Negative 3x over what? Over 5. So this is like negative 3 over 5 times x. Now, as x is infinitely large, think of an infinitely large number, and now multiply it by 3 over 5. Is it still a large number? Yeah. So that's infinity, but since there is a negative in front, this is negative infinity. So we can say DNE, negative infinity. Next, let's look at this one. Now, what is the reason why we're eliminating? Let's just repeat. What is the reason why we are able to eliminate those other factors? Right. And what I was looking for was basically that x is infinity. So can you do that for a limit as x approaches 457? No. Only when it's infinity. Only. Okay. So go ahead and do this one here. I'm gonna pause this and we'll come back. This is the limit as x approaches infinity. 7x cubed over 2x cubed. What happens to the x cubes? They go away. So this is just 7 over 2. That's the answer. That's the answer.
Oh, so much more easier than I thought.
So now,
My grammar.
so now, when we go back to this problem, right here, this says, what if g of a is x plus 1 over x squared minus 4? What if g of a is 0? And f of a is not 0? And I want the limit as x approaches a, f of x over g of x. So let's write that here for a minute. I'm just going to, oh, it went away. All right, so what was it? It was the limit as x approaches, what did it say?
As x approaches a,
A of
f of x over g of x,
f of x over g of x, and it,
g of a equals 0, f of a is not.
f of a is not 0, g of a is 0. Okay? So now, basically, what do we have here? We have some number over 0. We have some number over something that's approaching 0. Okay? So, some number, suppose it's a 5, over something that is approaching 0. So, let's think about this. Let's think about this. Something that is approaching 0, right? That's not really like that arrow. That's not proper notation, but I'm just doing it to explain. So imagine you have 5 pizzas, and you're gonna divide it between 5 people. How many does each get? 1. And what if you're gonna divide it between not 5 people, but 2 people? Does everybody get more or less? More. But what if you divide it by 1? More. Now what if you keep dividing it by less and less and less? So as the denominator gets smaller, what happens to the fraction?
It's bigger.
Get bigger. And if it gets infinitely small, the fraction will get infinitely big. So then something divided by 0 is infinity. Okay? So it's undefined, it's infinity. Okay? Mm-hmm. It's DNE, not undefined. DNE parentheses infinity. All right. Sorry, I'm going to stop here. For homework, you are only going to do up to number 47. All right, due Monday. And you have a quiz next week.
Do we have it on Wednesday?
It is on Wednesday.
Okay.